Okay, turn the light on. Alright, so now after going over 3.1, which was quadratic functions, we're going to talk about higher degree polynomial functions. Higher degree poly functions. Okay. Remember we did constants like f of x equals a constant. Its graph is a horizontal line, y equals c. And then we did linear functions, mx plus b, it's a slanted line. And then we just did quadratic in 3.1. Whether it's in general form or vertex form, it's parabola. So what happens if the degree is 3 or 4 or 5 or higher? That's what we're going to discuss next. We're going to talk about every possible feature in the next couple sections of a polynomial function. First of all, so to save some writing, I'm looking at the handout that I have in your notes. When we say a polynomial function of degree n, it's an xn, an minus 1 xn minus 1, an minus 2 xn minus 2, and then a2 x2 a1x plus a0. For instance, just to give you an idea, like if n is 4, so that polynomial p of x or f of x is a4 x4 plus a3 x3 plus a2 x2. So the exponents decrease by 1 until you get to the constant, which is a sub 0, and so on. Okay, that's called a polynomial function of degree 4. There's fifth degree, there's any degree you want. All the a's are real numbers, and of course, because the exponent, the highest exponent is the degree, its coefficient cannot be 0, because if it was, then the degree would be n minus 1, which is the next higher. So what are we going to do to have a polynomial function? We're going to go through several steps. Okay, the first one is not actually a step, it's observation. When you talk about graph of a polynomial function, it's a continuous and differentiable function, meaning no holes, no jumps, and no sharp edges. When you run your pencil, it's not going to cut you, you're not going to have a hole, and you're not going to jump. Okay, a graph of polynomial functions. So that's how you know when you have a graph of no sharp edges, no breaks in the graph. Okay, and no holes, none of that. Okay, so that's something we should know when we're graphing polynomial functions. Now the second one is a step which we're going to do first, the leading coefficient test, which is called the end behavior of the graph. When we want to graph anything, or we want to write anything in English, we start from left to right. So on the rectangular system of coordinates, left is negative infinity, right is positive infinity. So if I want to start graphing, I could, since I'm starting over here, I could start either in the second quadrant or the third quadrant, second or third. So this is a start, or right here, and I'm going to end graphing in one of these quadrants. Start, end. The leading coefficient test or the end behavior test is going to tell me where to start in the second or third quadrant, or where to end in the first or fourth quadrant. Okay, and that's why we're always going to say, as x goes to negative infinity, if I want to start all the way from the left side, is y going to be infinity or negative infinity? If y is positive infinity, we're going to start here. If y is negative infinity, we're going to start in the third. Now, same thing with x going to positive infinity, right there. Am I going to end the y being here, which is the first quadrant, or y being there, fourth quadrant? Okay, so this would be my second, this would actually be my first step. My second one is just observing. So let me go over examples about that before we go to the third step. So example 1, if f of x equals x cubed minus x plus 2. So so on the test, I'll just write that down for you. As x goes to negative infinity, y or f of x goes where? And as x goes to plus infinity, y goes where? Either positive or negative infinity. Okay, so it's called the leading coefficient test for a reason. When we're talking about x going to infinity or negative infinity in absolute terms, in absolute value, that's a huge number, right? Whether it's negative infinity or infinity, when you do absolute value, it becomes positive infinity. So it's like Gates and Warren Buffett. When you're talking about x going to infinity, it's a huge number. So x cubed, the highest degree, is gonna affect my answer, because if you're Bill Gates, who cares about if you lose a couple $1,000,000, right? Minus x plus 2. So when you're doing the leading coefficient test, when x is extremely large, all you care about is the leading term right there, the leading exponent. That's gonna decide whether your y value is going to be positive infinity or negative infinity. It's a matter of sign. If you put a negative infinity there and you cube it, you're going to end up with negative infinity, because negative 3 times is going to give you negative. If you do positive infinity to any power, it's positive infinity. So this tells me that when x and y going to negative infinity, it tells me I'm going to have to start right here. And when x and y are both positive infinity, we're going to end right there. Okay, one thing to know, when the highest degree is odd, when the highest degree is odd, like x or x cubed or x5 or x7, you're gonna start and end in opposite quadrants. We started in the third, we ended in the first. We couldn't have ended here because it would be along the same side. So when the exponent, the highest degree, is odd, you start and end, start and end. When that's even, you start here, you have to end there. You start here, you have to end there. Okay, that's good to know. Here's another example. Same thing. Negative x4 plus x squared minus 1. So what happens as x goes to negative infinity and as x goes to positive infinity? So again, the leading coefficient test says only this matters. So if I do a negative infinity to a power times a negative, when you do a negative to an even power, it turns into positive, but then that negative is gonna keep it in the negative infinity. So basically you're starting negative infinity, you're starting here, meaning you're gonna have to end there. Why? Because the highest degree is even, they're gonna start and end along the same side. If this was odd, then it would end there. Again, let's see. So I know as x goes to infinity, y is gonna be negative infinity. You can check. Infinity to the fourth power infinity times negative is negative infinity. Okay, so that's just gives us insight about where to start and where to end. Then the next step. So I showed you step 1 and 2 on the handout. Actually, there's more handout, but it's not in there. So I'll write it down. So after doing that test, then we're gonna find the zeros. This is the most important step. Find the zeros of a polynomial function. And the zeros are actually the x-intercepts of the graph. In this case, if it's possible, we're gonna factor. If not possible, then that's gonna be next section. So by factoring, it should work in this case. Okay, so and once we get those zeros, then we're gonna look at the following expressions are equivalent. The following steps are equivalent. C, because we're going to be saying this all the time, C is a zero of a function f. So a zero of a function, that means equals C is a solution of the equation f of x equals 0. Just to give you an idea, like if I have f of x equals, let's look at something we know, minus x minus 3 quadratic, which we did. So if I want to find the zeros of f, that means x squared minus x minus 3 equals 0, x minus 3, x plus 1 equals 0. So we get x equals 3, x equals negative 1. So C is a zero of f, like 3 is a zero of f. That means x equals C is a solution of the equation. We do this all the time, but we don't write it down this way. And also, if x equals c is a solution, then x minus c is a factor of f of x. A 0 will give me a factor will give me a 0. That this was a factor, it gave me a 0. This is a 0, it gives me a factor, because this is what? X minus 3, x plus 1. If x equals 3 is a 0, x minus 3 is a factor, x negative 1 is a 0, x minus negative 1, which is x plus 1, is a factor. And it's an x-intercept of the graph, which I just said it there, but I want to write it down. X equals c is an x-intercept of the graph of f. So these are all the same, but just we never put it in writing. So we have that. Again, they might ask about these in a different way. So when we say find the zeros, find all zeros, so, or x-intercepts or solutions of f of x equals x cubed plus 3x squared minus 4x minus 12. So to find the zero, set that equals 0. It's like finding the x-intercepts. And remember, we're going to try factoring since we have 4 terms. So we're going to do grouping. X squared, x plus 3, minus 4 times x plus 3. And x plus 3, x squared minus 4 equals 0. This is the difference of 2 squares. Each factor gives me a 0. X plus 3 equals 0, so x equals negative 3. X equals 2. So we know the graph is going to cross the x-axis just at these 3 values, at 2, at negative 2, and negative 3. Okay? So we're doing the piece by piece. At the end, we're going to put all the pieces of the puzzle together so we can get the graph to the best of our ability at this point. So step 1 just tells us what you should expect to get when you're graphing a polynomial function. Step 2, it tells us where to start and where to end behavior of the graph by assuming x goes to negative infinity and x goes to infinity. Step 3, to find where the graph crosses the x-axis. Step 4, determine the shape of the graph. That's very important. Determine the shape of the graph near its zeros. The shape of the graph near its zeros. Have you ever wondered why f of x equals x squared bounces off at its 0, whereas f of x equals x cubed, it goes through the x-axis at its 0? There's a reason. This has an even power, this has an odd power, and that's what we're going to talk about right now. If x minus c appears m times, m is a counting number, in factoring f of x, then m is called the multiplicity of c in that factoring. For example, f of x equals x minus 2 squared times x plus 1 cubed. You can see that multiplicity of x equal 2 is 2, and the multiplicity of x equal negative 1 is 3. Even, odd. That tells you, what's going to happen with the graph. If m is odd, then the graph is going to cross the x-axis. It's going to go through the x-axis. And if it's even, then it's going to bounce off at the x-axis. Okay? So even multiplicity means it's going to bounce off. Odd multiplicity means it's going to go through. And what's really more important is the bigger the power, the more the hugging. Seriously. Look, at x squared, it barely touches and bounces off. If you do x to the 4, you can try this with your graph, or x to the 4. If you do x to the 6, there is more hugging. Like x, f of x equals x, there's barely any hugging. If you do x cubed, you saw x cubed. If you do x to the 5, it's going to be more hugging. Okay? And so on. Okay. And I just want you to, we just did this. I want to show you that at -1, it's going to go through, it's going to hug it there, and then it's going to bounce off. Let's see that on the graph. So y equals x plus 1 cubed times x minus 2 cubed square. So you can see at -1, and then what happens at no, sorry, at -1, what happens at 2? It doesn't see what, okay, let me change the window, it's messed up. Let's do -5 to 5, and then 1. I gotta fix my window, it's messed up. So at -1, there's going through, and at 2, it bounces off, okay? So the next step, local extrema. So remember when we say local extrema, meaning local max or local minimum of a polynomial function, if f has a poly function, or is a, sorry, of degree n, where n is a counting number, then the graph of f has at most n minus 1 local extrema. So for example, something like this could not possibly be x squared, because x squared would have at most 1 extrema. Okay, it could be x cubed, because x cubed has at most what? 2 extrema. This has 2, at most could be 2 or less. Okay, so keep that in mind. Is this could be x cubed, x to the 4, x to the 5? We don't know. Okay, but it could be. Now anything like this has 3 extrema, so it could be, it cannot be the 3rd degree, it has to be a 4th degree or a 5th degree, and so on. So now we're going to piece all this together. So we're going to graph the poly function based on what we know, x cubed plus 3x squared plus 4x minus 12. Okay, remember the first thing we're going to do is we're going to do the end behavior as x goes to -infinity. Why? We're going to only look at the highest degree, and -infinity to the 3rd power is -infinity, and as x goes to infinity, again goes to infinity, so we know the graph is going to start here and it's going to end infinity there, and we knew it's going to end there because it's an odd exponent. It starts and ends in opposite quadrants. If it was even, it starts and ends in the same side. Okay, so we got that, and then the zeros, we already got the zeros. We did that previously today. So these are the zeros. They all have multiplicity 1. So the graph will go through these. They will go through these zeros. And that's not much that we know. I mean, that's all we could do. The intercept, we found the intercept. The y-intercept is when x is 0, y is -12. So let me give you an idea what we know. We know the x-intercepts are -2, 2, and -3. -2, -3, and 2. We know it's going to start here and end there. We know it's going to hit the y-axis at -12. -12. So it's going to start here, it has to go through this, it has to go up because it come down. We don't know how high up it goes. It has to go down, and then it has to go all the way down, hit -12. We don't know where it's going to stop, if this is a minimum or no, we don't know. And then up, and then remember it starts here and ends there, so it's going to have to go there and never come back, because if it came back then it would have to hit the x-axis, which we know it can't. All right, a very important piece of information: how do we find those maximum and minimum? That's something we couldn't possibly do without technology at this point. We need calculus, and we don't have the calculus for it. That's what the derivative is all about, okay? So this has to wait till we get to calculus, but we can find the zeros. We can tell how the graph behaves around the zeros. We can find the intercepts. We can find where it starts and where it ends. That's about what we can do right now. Here's another one. How do we graph the function f of x equals x to the 4 minus 3x cubed plus 2x squared? So let's start with the end behavior. As x goes to -infinity, y goes to, if we do -infinity to a 4th power, that's positive infinity. And as x goes infinity, y is infinity. So it starts, it's in here. And since that's even, it has to end there, as this says, okay? Then we want to talk about the zeros of f. So x to the 4 minus 3x cubed plus 2x squared equals 0. We can pull out x squared. And then factor this, x minus 2, x minus 1, x squared. So we have x equals 0. The multiplicity is 2. We have x equal 2, multiplicity is 1. We have x equal 1, multiplicity is 1. So we know the graph has to bounce off, and then it has to go through. It goes through the graph, bounces off. And then the y-intercept, when x is 0, if you put a 0 in there, it's y equals 0, the origin. Okay, so that's all, right? We got the multiplicity. We know there's gonna be at most three extrema. Okay, that's what we know. So to graph it, let's label the intercepts or the zeros: 0, 2, and 1. It's gonna go through 0. It's gonna go through 1. It's gonna go through 2. Now it's gonna start here and end there. So start here, it's gonna go through 0, 0. It's gonna bounce off at 0, 0, right? We know that. And then it's gonna go up. We don't know how much up because we don't have the maximum, so we don't know. And then it's gonna come back down. It's gonna go through that, as we know, down, and then go back up, and it has to end here. Okay, and you can do 42, page 266 on your own, okay? And that's it for 3.2.